has started. This week, we will start learning thermodynamic cycles. The first part of the thermodynamic cycles are vapor cycles. So when we say vapor cycles, they are either vapor power cycles or vapor refrigeration cycles. Then next week, we will continue with gas cycles. The difference between the vapor cycles and gas cycles are in vapor cycles, the working fluid, for instance, water, alternates between liquid and vapor, whereas in gas cycles, the phase of the gas does not change. For instance, in the case of an internal combustion engine, the working fluid is always a gas. So remember that we have seen a power plant in the beginning of the course. A power plant is a special plant that generates energy, electrical energy, and mostly using one of the power cycles, such as a vapor cycle. In a vapor cycle, remember that we have four elements. One of the elements is a boiler in which water is converted to vapor, liquid water is converted to vapor. Then vapor goes into the turbine, rotates it, and as the turbine rotates, it also rotates an electric generator, which generates electricity. Then, when the vapor leaves the turbine, it's still a vapor, but a low pressure vapor. So in order to send this low pressure vapor back into the boiler, it's necessary to make liquid, condensate it. So in order to condensate it, it's cooled in a heat exchanger called condenser. So as it passes through the condenser, it becomes liquid, and then it's pumped into the boiler back again, so the cycle is completed. According to the second law, remember that it's not possible to convert all the heat energy to work. Also here, we can see the same thing. We use fuel and air. It could be coal, it could be any kind of petroleum product. It could be either nuclear energy. Whatever the energy is, this energy is transferred to the water to vaporize it. And as the water is vaporized, only part of the enthalpy or energy of the water can be converted to work in the turbine, and some part of the energy must be rejected in the condenser, otherwise it's not possible to make a complete cycle. So for the cycle to be complete or to be repeated, it's necessary to reject some energy at the condenser. So if you look at the directions of the energies, you have Q in here, then you get work out here, and some of the heat must be rejected to make the water vapor liquid. So this is Q out. There is a little work here to be added into the pump, but it's very small when compared to the work out here. So pump work is almost 1% of the turbine work. So most of the time it can be neglected. So once, for instance, the coil is burned here or the fuel oil burned here, some of the gases, the combustion gases are released from a stack, and it means that not all the energy of the fuel has been converted into the vapor energy. Most of the time, this conversion is about 90% or more. So the 90% of the energy of the fuel is converted to vaporize the energy, and uh, maximum something around 30% of the enthalpy of the vapor can be converted to work here, and the remaining 70% must be rejected in order for the cycle to be complete. The way we operate the condenser, which is a heat exchanger, is to use cooling water. If the plant is nearby a sea or nearby a lake, then the cooling water can be taken out from the lake or from the sea directly to make the water liquefied or condensed. Otherwise, if the plant is far away from a lake or far away from a sea, then cooling towers can be used. The method, the principle of the cooling tower is like this. As the water is heated inside the heat exchanger because it has condensed the vapor here, then it's heated a little, then this heated water is sprayed inside the cooling tower. As the water is sprayed into the cooling tower, it evaporates because of the air flowing around it. So there is a natural airflow inside the cooling tower, which evaporates some of the water sprayed here. And as the water is sprayed and evaporated, it absorbs some heat from the air. So because of this evaporative cooling, we will call it evaporative cooling. Let's say the water sent here is 35 Celsius, and it comes back to the condenser, just as an example, as 22 Celsius. So the amount of energy lost here is due to the vaporization of the sprayed water here. The shape of the cooling tower is unique because when you have a shape like this, we will see it in fluid mechanics, then we know that air must accelerate. The accelerated air will have a lower pressure, and lower pressure will make the air move up. So there is no fan at the top, as you can see. Without any device to move the air can move by itself from the bottom of the tower to the top of the tower only because of the shape of the tower. Of course, the temperature here is higher than the temperature there because uh, higher temperature means that lower density. Lower density means that it will be subjected to buoyancy forces and it will raise. So we are interested in power plant itself, not the whole thing, but only the vapor cycle itself. In a vapor cycle, as I said, we have a boiler in which we add heat. Then, as the heat added into the liquid water, here we have liquid, the liquid water becomes vaporized, and at the exit of the boiler, it's a vapor. So as it passes through the turbine, it rotates it, giving us a turbine work. And as it leaves the turbine, it's still a vapor, but at low pressure. Whereas this one was at high pressure. Then it means that we have basically two types of pressures in a vapor cycle, one high pressure and one low pressure. So a vapor cycle is operated between two pressures. So this low pressure vapor passes through the condenser, which is just as a heat exchanger, and because of the cooling here inside the condenser, it becomes a liquid here again. But this liquid has still the same pressure. It's a low pressure liquid, and when it's pumped back into the boiler, its pressure is increased. So the liquid here has high pressure. So as a summary, we can say that there are only two types of pressure in a steam cycle, one low pressure, one high pressure. The low pressure sections of the cycle is the exit of the turbine as well as the exit of the condenser. The high pressure sections of the cycle is the exit of the pump and exit of the boiler. If we write the energy equation for open systems for any device, we can obtain, this is just for any device, for instance, for turbine, we can obtain this. It's in steady state, so in steady state, the change of energy per unit time is 0. So the left-hand side of the equation is 0. So this is what happens in steady state always. The left-hand side of the equation is 0. Then we have heat interaction in the turbine. For the time being, we assume that the turbine is well insulated. It's an adiabatic turbine, so there is no heat interaction between the turbine and the surroundings. So it's not losing heat, it's not gaining heat, it's well insulated. It delivers energy, of course, so we have the work term here. Then the working fluid, because it's an open system, will have enthalpy, kinetic energy, and potential energy. For many kinds of power cycles, steam power cycles, we assume that the change in the kinetic energy can be negligible and change in the potential energy can also be negligible, so that the turbine work per unit time, per unit mass is just the difference of the enthalpies entering the turbine and exiting the turbine. So if you calculate the enthalpy here and at the exit, then you can calculate the turbine work by just subtracting two enthalpies from each other. And this is W dot 1 divided by M dot, which means it's kilojoules per kilogram. If you multiply this by M dot, which is kilograms per second, you get kilojoules per second, which is kilowatts. So depending on your calculations, you can get an energy result here, or you can also obtain a power result by M dot times delta H. Similar things, similar kinds of energy balance can be written for all the members of the cycle. In the condenser, if you write this energy equation for the open system as a condenser, you will get the condenser heat to be just the difference of enthalpies entering the condenser and leaving the condenser. Similarly, the pump work is just the difference of the enthalpies leaving the pump, entering the pump, and leaving the pump. And similarly, the heat added inside the boiler is just the enthalpy difference of the liquid entering the liquid leaving the boiler minus, sorry, this one is vapor leaving the boiler minus liquid entering the boiler. So as you can see, for the sake of simplicity, we are not using the kinetic energy changes or potential energy changes, or we just simply say that the For the work terms, we get the Q to be 0. So for work terms, we take Q to be 0, and for Q terms, we take work to be 0. So in boiler and condenser, we take work to be 0, and in turbine, we take work to be 0, and in turbine and pump, we take Q to be 0, because we assume that turbine and pump is adiabatic, so there is no heat exchange with the surrounding. And for boiler and condenser, there is no work interaction between the boiler and condenser. So that's why for all the items, or for all the members found in the vapor cycle, the calculation is made only by the differences of enthalpies, which makes the calculations very easy. So by having the works and Qs inside the power generation cycle, steam power generation cycle, now we can calculate the efficiency of the system. Remember, efficiency is always some output divided by some input. Here the output is the network. So output is network, which means turbine work minus pump work, because we obtain turbine work, but we have to deliver pump work. And input is the boiler heat. So when you write the efficiency in terms of enthalpies, you get an equation like this. Or you can also write it as in terms of Qs. By the way, it's also possible to relate the pump work to turbine work, which is called back work ratio. Back work ratio is the necessary work or necessary power to be delivered to pump divided by the work delivered by the turbine. And as I had already mentioned, that this is most of the time less than 1%. So back work ratio is most of the time less than 1%. Is a power cycle, steam power cycle. But it can be as high as 50 or 60% in a gas turbine, which is a gas cycle. We will see it next week. But in power cycles utilizing steam, the back work ratio, which is the ratio of the necessary pump work divided by the turbine work, is only 1% or less than 1%. Normally, we may use saturated vapor in a vapor cycle. So when we use saturation vapor, the output of the boiler is saturated vapor. So this one here is saturated vapor. And when it passes through the turbine, which is isentropic, because turbine is adiabatic and reversible, which means it's isentropic. You can see the isentropic relation here, because this is entropy, so you can see that the entropy does not change when it expands inside the turbine. So at the exit of the turbine, it gets into the condenser, where its phase is converted from gas or mixture of gas to liquid. So here we have saturated liquid. Then in the pump, its pressure is increased to the 0.4, which is subcooled or compressed vapor, compressed liquid. Then inside the boiler, first it's heated to the saturation temperature. Then as this phase change takes place, it becomes a saturated vapor. So you have saturated liquid here at high pressure, and at the exit of the vapor boiler, you have saturated vapor. This is called a cycle with saturated vapor. On the other hand, it's also possible to heat the vapor further so that you can obtain superheated vapor. In some vapor cycles, there is a section inside the boiler which is called superheater, and inside the superheater, the saturated vapor can be heated up to a higher degree of temperature, which is called superheat temperature. And when we use superheat vapor, you can see that the exit of the turbine is drier than the exit of the saturated vapor turbine. So the reason why we are using superheated vapor is both to increase uh, the efficiency, and also we would like to have a boiler that does not work with the liquid droplets inside the steam. So we would like to have the steam to be as dry as possible. In a cycle, remember that net work is equal to net heat is equal to net work in a cycle. And here, the area under the TS diagram is just net heat. So Q net is obtained from the area under the TS diagram, which is also equal to net work. So as you can see, the area under the saturated vapor curve here is less than the area under the superheated vapor case, which means by superheating, not only we are protecting the turbine from wet vapor, but also we are increasing the work, which means also efficiency. The pump work, because the pump uses liquid inside it, can be calculated from not only enthalpy differences, but also from the equation of the work in open systems. In the open systems, the work can be calculated by the integral of VdP. And because both the entrance and the exit of the pump is liquid, we can assume that the specific volume does not change. So we assume that it's constant, so that the pump work can be written as just V3 times the delta P, which is also equal to enthalpy difference, which we have already mentioned in the previous slide. So the pump work is calculated either by using the enthalpy differences or by using V3 times the difference of the pressure between the inlet of the pump and exit of the pump. There is a numerical example here in which we are given a vapor cycle which use saturated vapor. How do we know this? The exit of the boiler is saturated vapor. There are two pressures, as I said. One pressure is 0.008 megapascals, which is a very low pressure. It's a vacuum pressure. It's less than atmospheric pressure. We need to have less than atmospheric pressure because when the pressure is low, remember that the saturation temperature is also low. So we can have a saturation at a much lower temperature if the pressure is also low. And the second pressure is the boiler pressure or the turbine inlet pressure. So this is one pressure here. So this is one pressure here. And this one is the second pressure. So it works between 8 megapascals and 0.008 megapascals. At the inlet of the turbine, we have saturated vapor. At the turbine, we have saturated vapor. At the exit of the turbine, we have mixture. At the exit of the condenser, we have saturated liquid. And at the exit of the pump, we have subcooled liquid, or sometimes it's called compressed liquid. So we would like to calculate the heat added in the boiler, work obtained from the turbine, heat rejected in the condenser, and also work to be delivered into the pump, which is less than 1% of the turbine work. This system produces power of 100 megawatts. So it's actually the mass flow rate of the vapor times the network in the system. The first part of the question is asking the thermal efficiency. So eta is W net divided by Q in. The first part. The second part is asking the back work ratio. So back work ratio is turbine pump work divided by turbine work. The third part, mass flow rate of the steam, which is this. Then the rate of heat transfer into the working fluid as it passes through the boiler, so Q in, this. Then the rate of Q transfer, heat transfer, Q condenser, this, rejected heat. And if the mass flow rate of the condenser cooling water. So we have found out the mass flow rate of the water. It's also asking the mass flow rate of the cooling water in the condenser. And because it's a heat exchanger, you remember from previous weeks, in a heat exchanger, Q heat should be equal to Q cooled, because heat transfer from one side will be taken from the other side. So if you know the Q condenser here, it should be also the heat taken by the heat, which will be calculated from just MC delta T. So the first thing to do is to find the states of the different locations, different states of the cycle. So the first state, which is the exit of the boiler, is saturated vapor. So we have saturated vapor. at 8 megapascals. So we need to go to the saturated vapor table and can read all the values such as H1, the entrance of the exit of the boiler, which is the inlet of the turbine, and S1, which is equal to S2, because in turbine, remember that the expansion is isentropic, so the S1 value will be equal to S2 value, which is the exit of the turbine. So from the table, we find the exit enthalpy of the boiler as 2758 and exit entropy of the boiler to be 5.74432. Because S1 is equal to S2, and remember that for a mixture, we can write S as SF plus the quality S gas minus S fluid. We know this because it's equal to S1, and we need to find the SF value and S gas value, and they are actually the saturation vapor at lower pressure. So from table again, we can read SF, the liquid entropy, and S gas, the gas entropy. Once we read them, we can calculate the quality of the steam that leaves the turbine. So the quality here, quality of the mixture is calculated from the equation shown here. The quality of the steam exiting the turbine is 67%. So it means that 67% of the fluid that leaves the turbine is vapor, and the remaining 23% is liquid, water droplets. So once we have this quality, we can also calculate the enthalpy at the exit of the turbine. We will use a similar kind of equation. The HF value and HF gas value are taken from the table, again at the same pressure at 0.008 megapascals. So we calculate the enthalpy of the exit of the turbine. So we know the enthalpy at the inlet of the turbine, at the exit of the turbine, meaning that we can calculate the work in the turbine, because the work in the turbine is just the difference of the enthalpies. So it's just H1 minus H2. And it's also equal to W dot turbine divided by the mass flow rate of the steam. We are given this value as 100 megawatts. We can calculate the difference here. So we can easily find the mass flow rate of the steam. Also, at the inlet of the pump, which is the exit of the condenser, we can take the enthalpy of the fluid enthalpy, liquid enthalpy, because the fluid leaves the condenser as saturated liquid, so we can read it as saturated liquid enthalpy. And from here, we can also calculate the exit of the enthalpy, exit of the pump from the pump work divided by N, which gives you W pump. And because the pump work can be obtained from either by the differences of the enthalpies between the inlet and exit, or by V3 times the difference of the pressures by V3 times the difference of the pressures. We know V3, which is equal to specific volume of the saturated liquid. We know the difference of the pressure. One pressure is 8 megapascal, the other pressure is 0.008 megapascal. So we can calculate the enthalpy at the exit of the pump. So this is the exit of the pump. So once we have all the enthalpy values, now we can calculate all the necessary efficiency kind of or heat kind of calculations. The cycle of the work is the net work, which is the turbine work minus pump work. The turbine work is obtained from this. The pump work is obtained from here. The boiler heat is obtained from there. So the efficiency is just W net divided by Q in. So we find the efficiency of the system to be 37%. It means 37% of the energy added in the boiler can be converted to work. What happens to the other 63%? 63% is just rejected in the condenser. Otherwise, as I said, according to the second law of the thermodynamics, it's not possible to have a complete cycle or cycle that repeats itself. The back work ratio is the ratio of the pump work divided by the turbine work, and as you can see, it's less than 1%. This is most of the time the case. The ratio of the pump work to the turbine work is most of the time less than 1%. Mass flow rate can be calculated from, which have already been written as because net work is equal to W dot net divided by mass flow rate. Here we can obtain the mass flow rate, and you can see that the mass flow rate is 3.77 times 10 to the 5 kilograms per hour. Here, with this mass flow rate, we can also calculate the Q in, because Q dot in is equal to mass flow rate times H1 minus H4. It's 269.77 megawatts. And the rejected heat at the condenser Q out is the same mass flow rate of the vapor, but this time we are going to use the enthalpy differences as H2 minus H3. So you can see that the ratio of the Q out to Q in is 72%. So 73% is rejected. This part is rejected because it's necessary by the second law of thermodynamics. The cycle work can also be calculated from the difference of the net heat. As you can see, we can calculate the condenser work from this equation, the condenser heat from this equation. The condenser heat is calculated as the same, so 169 megawatt, 169 megawatt. And it has to be equal to the mass flow rate of water times Cp of water times delta T of water. Because it's a heat exchanger, as I said, the heat transferred from one side must be equal to the heat received from the other side. So by doing this calculation, this is the thermal balance of this heat exchanger, the condenser. In the condenser, we have a steady state situation where the time rate of change of energy is 0 because it's steady state. The condenser itself is insulated. So we have steam here and water here, but it's well insulated out, so there is no heat exchange with the surrounding, so that it's 0. It doesn't do any work, it's 0. And the incoming uh, water and the difference between the incoming water and exiting water is calculated from this, and the heat transferred from the steam is this. So you can just do the energy balance. So you can calculate the mass flow rate of the water from here. This is almost equal to Cp times delta T of water. So you can use either the enthalpy differences for liquid water, or you can just use Cp times T as the enthalpy. So by reading the enthalpies of the water, this is the inlet enthalpy, this is the exit enthalpy of the inlet minus exit. Okay, that's correct. So at the numerator, we have the condenser heat. So you can see the mass flow rate of the water is 7.3 times 10 to the 6th. When it's compared to the mass flow rate of the water, is much greater than mass flow rate of the steam is much greater than the mass flow rate of the steam. If you compare it, you will see that the difference between them is about 30 times. So the mass flow rate of the water is almost 30 times the mass flow rate of the steam, which is a very typical situation, because in steam we have a phase change, so mass flow rate is small because it's latent heat. But for the case of cooling water, it's sensible heat, so that there is no mass phase change. In this case, we are going to use the temperature changes, meaning that the mass flow rate of the cooling water must be much greater than the mass flow rate of the steam. And in this specific problem, it's about 30 times the mass flow rate of the steam is equal to the mass flow rate of the water. So how did you find the solution? Was it complicated? Was it okay? Any comments regarding the difficulty of the solution? I wonder if you are there or if you're listening. Okay, anyway, I will continue. So, we would like to have as high as possible efficiency, because by having efficiency, we can save a lot of fuel, meaning that a lot of money. Also, we can protect the environment by consuming less fuel, especially fossil fuel. So what are the methods to increase the efficiency? As you see, the efficiency is related to amount of work. As the amount of work is increased, then efficiency is increased also, because by definition, efficiency is net work divided by the Q in. And suppose that Q in is constant, then if we are able to increase the network, then it's possible to increase the efficiency. And network is the area under the TS curve. Because in a cycle, net work and net heat is equal. So if you look at this, net work and net heat is equal. So if you look at this TS curve here, this is the first case in which you have an area like this. In the second case, where you have a higher pressure, then you have an area like that. And it looks like the area in the second one is more than the area in the first one, meaning that the area, the work in the second case is greater than the work in the first case, meaning that the efficiency in the second case is greater than the efficiency from the first case. So our objective is to increase the work so that the efficiency can also be increased. Another way is to be decreasing the condenser pressure. So in the first one, you have an area like this. In the second one, if you lower the condenser pressure, you have a larger area, meaning that also here, if you have a lower pressure, you have a higher work or higher efficiency. So if boiler pressure is increased or condenser pressure is decreased, then we know that the work can be increased, meaning that the efficiency can also be increased. Any questions so far? Okay, we're going to have a 10-minute break, and we will be back at 2 o'clock, 2 a.m., 2 p.m. So in the beginning of the chapter, we said that most of the time we can assume reversible systems for turbines and pumps and reversible boilers and condenser. For the boiler, turbines and pumps, we can also assume that they are adiabatic. So when they are both adiabatic and reversible, it's called isentropic. So isentropic means that it's both reversible, meaning that there are no irreversibilities inside, such as friction, and adiabatic, meaning that there is no heat exchange with the system, turbine, or pump, and the surrounding. But in real life, there is no such thing as adiabatic or reversible, because most of the time we can at least have some irreversibilities inside the turbine or inside the pump, which will cause the entropy to be increasing. So this is for an actual turbine in which entropy is increasing, or this is for, again, actual pump in which the entropy is increasing. The reason why entropy is increasing because of the irreversibilities inside the pump or turbine, such as friction between the fluid and turbine blades. So when this happens, because it's a loss of available energy, the actual turbine work is less than reversible turbine work. This is for turbine, because it means that it will deliver less work than the reversible turbine, But for the pump, it's opposite. For the pump, the actual pump work is greater than reversible pump work because an actual pump requires more work than the reversible pump. So by taking into account the reversibilities, we can have isentropic efficiency for turbine. The isentropic efficiency of turbine is the turbine work divided by the isentropic turbine work. So isentropic turbine efficiency is equal to actual turbine work divided by the isentropic turbine work. On the other hand, isentropic pump efficiency is written in a reverse way. It's isentropic pump work divided by actual pump work. So, of course, their efficiencies, they must be less than or greater than 1. So if it's equal to 1, it means that it's an isentropic pump or pump or turbine. Otherwise, uh, it's a pump or turbine with irreversibilities inside. For the turbine, use this. And for the pump, you need to use that. There are other non-idealities, such as there may be pressure drop inside the boiler because of the fluid and pipe friction, or there can be also pressure drop in the condenser because of the friction of fluid and the surfaces inside the condenser. There can be irreversibilities in transferring of the fuel energy to the water because, as I already mentioned, almost 90% of the fuel energy is transferred to the water. The remaining 10% has to be rejected from the stack. So these are the other types of non-idealities or irreversibilities that can affect the efficiency of a system. Here we have an example that has turbine and pump which are not isentropic. It means that they have irreversibilities inside, so that the turbine exit has a increasing entropy. So this is the isentropic case where the entropy remains the same. This is the real case, actual case, where the entropy is increasing. And for the pump as well, this is the isentropic case, and this is the actual case. So here we're going to obtain less turbine work because of the irreversibilities, and we have to deliver more pump work because of the irreversibilities again. Note that the pressures are still the same. The condenser pressure is 0.008 megapascal and the boiler pressure is 8 megapascal. By using the irreversibilities in turbine and pump, we can now recalculate the work generated by this vapor cycle, vapor power cycle. So the efficiency of the isentropic of the efficiency of the turbine is defined as the isentropic turbine work divided by the actual turbine work. No, actual turbine work divided by the isentropic turbine work. So we can calculate the actual turbine exit as opposed to isentropic exit from this equation. So the actual turbine exit is greater than the isentropic turbine exit. Because what happens is, because of the irreversibilities such as friction, the steam leaves the turbine at a higher energy. So instead of converting all the energy to work, or a lot of the energy to work, some of the energy has been converted to enthalpy increase because of the friction. So similarly, the pump isentropic efficiency is given as the isentropic pump work divided by the actual pump work. So from here, we can calculate the actual pump exit enthalpy, which is higher than the isentropic pump enthalpy because of the same reasons again, because of the irreversibilities such as friction, the fluid friction and the pump impeller. We have a higher enthalpy at the exit of the pump than the ideal case, the isentropic case. So we can now recalculate the actual cycle work as opposed to isentropic cycle work. When we calculate the actual cycle work and find the efficiency, we find that efficiency has dropped from 37% to the 31%. So this is less than the isentropic pump and turbine. And the mass flow rate is found to be higher than the isentropic one because in order to obtain the same 100 megawatt power, we have to use more energy because of the overcoming of isentropic, overcoming of the irreversibilities. So this is greater than the isentropic one. And it can be seen that because of the irreversibilities, because we are losing some of the energies to the irreversibilities, we have to supply more energy in actual case than isentropic case, always for the same reason. So this is greater than isentropic heat input. And in condenser also, we need to use more cooling because of the increasing entropies. The fluids are living at higher enthalpies. Then we have to use more cooling. Then in this case, it's also greater than isentropic case. And the cooling water, for the same reason, because we have to have a higher cooling in the condenser, then it means the mass flow rate of the water must be greater than the isentropic case. So as you can see, because of the irreversibilities in the pump and the turbine, we have to use more cooling, more energy, and it's all because of the irreversibilities found in the turbine and the pump. Now, up to now, we have studied a vapor cycle which is operated under saturated cases. So it's also possible to have a separate section inside the boiler and to heat the steam over the saturation temperature so that the steam can be superheated. So by adding some more heat, instead of saturated vapor, we can make it superheat by heating the vapor, by adding more energy to the vapor. And what kind of benefits can be obtained from this? As you can see, in the superheated case, the work is greater than the saturated case. Also, another advantage is in the superheat case, the turbine is operated with drier steam. So the exit of the superheated gas is greater than the saturated one, which means turbine is operated with drier air and drier steam, which is preferable for a steam turbine. So this is how the superheater works. This is actually reheat cycle, not superheater. Superheater is just another section inside the boiler. This is a reheat cycle. In the reheat cycle, we have a two-stage turbine. We have high pressure turbine and low pressure turbine. So as the steam gets into the high pressure turbine and some work is obtained, so here we obtain some work called low pressure turbine work. Then it's sent back to the boiler again. As you can see, the exit of the turbine, the low pressure turbine, is at some other pressure, so we don't know the pressure here, so it's an intermediate pressure. And it's sent back to the boiler again, and it's heated up to some superheat temperature, then gets into the low pressure turbine. So the total turbine work is the summation of high pressure turbine and work is the summation of high pressure turbine and low pressure turbine. So we have high pressure turbine plus low pressure turbine as the total turbine work. Then the rest of the cycle is just the same. It gets into the condenser. Q condenser is rejected, then it's pumped back into the boiler again. So what happens is, this is the exit of the boiler, the normal exit here. It gets into the first turbine. So this is the first turbine, high pressure turbine. Then at the exit of the turbine, it's sent back to the boiler again and heated to some other temperature. It can be same as the first boiler temperature, but it doesn't have to be the same. It's heated up to another superheat temperature, so it enters low pressure turbine. Then we have another work from low pressure turbine. So as you can see, the exit of the low pressure turbine is now 0.4. So if there was no reheat, the exit of the first turbine would be there. But in this reheat cycle, the exit of the low pressure turbine or the inlet of the condenser is here, meaning that it's drier than the case without reheat. So this is the only difference between a cycle which doesn't have a reheat. So you just need to sum the turbine works to get the total turbine work, and the rest of the calculations are the same. An example is given here. According to the example, the boiler outlet pressure is the same as the previous problems, 8 megapascals. Temperature is given as 480. As you can see, because it's superheated vapor, we have to have two properties. In saturation, you need either pressure or temperature. But in superheat, you need two properties. For instance, pressure and temperature, or some other. So because it's superheat, two properties are given. The exit of the boiler is 8 megapascals, 480. So it's 8 megapascal, 480. This is 480 Celsius. It enters the first turbine, it expands to a lower pressure while it produces a work. Then it gets back into the boiler again, the reheat cycle. So this is the reheat cycle. And as you can see, the reheat pressure is lower than the normal pressure. And in this case, it's heated to some other temperature. So 440 Celsius. So it's heated to 440 Celsius. And at 0.8 megapascal. Then it expands into the condenser pressure, which is exactly the same as the previous ones. So we have two turbine works. First this one and that one. We have to sum them up to obtain the total turbine work. Then the rest of the cycle is exactly the same. So for the first turbine, as it expands through the first turbine, the high pressure turbine, we can calculate the entropy because the expansion, it's an isentropic turbine without any reversibilities, so that the entropy at the exit of the turbine is the same as the entropy at the inlet of it. So S1 is equal to S2, S3 is equal to S4. So we can write the equality of the entropies. S1 is equal to S2. It's an isentropic turbine without irreversibilities. And S3 is equal to S4. We are going to use them to find the properties at the exit of the turbines. So for the first turbine, the inlet of the first turbine is 8 megapascals and 480. So from the superheat table, these are from superheat table, we get the inlet of the turbine, which is the exit of the boiler, and inlet of the turbine entropy, which is equal to exit of the turbine entropy. It's expanded to a lower pressure. So if you look at this, it's expanded to a lower pressure here, and it's a mixture of vapor and liquid. So we have to find the quality of the first turbine exit first. The first turbine exit quality is 98%, 99%. It's almost dry, but we will use this quality. It's almost dry, but we will use it. So by using this quality at the exit of the first turbine, the turbine exit entropy is found to be 2743. Similarly, we will calculate the quality at the second turbine exit by using this. The inlet conditions of the second turbine is 0.7 megapascals and 440 Celsius, so that we can read from the table H3 as well as S3, which is equal to S4. So we can calculate the quality at the exit of the second turbine, and the quality of the second turbine exit is 94%. So from here, we can calculate the enthalpy at the exit of the second turbine. So far, we know H1, H2, H3, H4. So we calculated them or read them from the tables, superheat tables. Now, the cycle work, the net cycle work is the work of the turbines minus the pump work. Pump work is little, but we're going to consider it anyway. The pump work for the first pump is H1 minus H2. The second one is H3 minus H4. And the pump work is H6 minus H5. And the net Q addition is the normal boiler heat plus superheat. So the efficiency is always W net divided by Q in, the total Q in, because some part of it comes from the boiler heat, the second part comes from the superheat. So by calculating this, we obtain an efficiency of 40%, which is less than the saturated steam system, because in saturated steam, I guess it was 37%. Now it's gone up to 40% because of the use of the superheat. We have increased the efficiency of the system. Also, by increasing efficiency, this is less than the previous one, the mass flow rate. Less fuel and less mass flow rate of the steam is required to obtain the same 100 megawatts, because we have a higher efficiency. Then the cooling water is also less than the saturated one, because we have a higher efficiency, meaning that the rejected heat can be less. Less rejected heat means that we need less cooling water. So, as an extension to this problem, we now assume that the turbines have some irreversibilities. Both the first turbine, high pressure turbine, and the second turbine, the low pressure turbine, has some irreversibilities, so that we now know that they will produce less work than the isentropic turbines because of the irreversibilities, such as friction of the steam and turbine blades. So in this case, we are given the isentropic efficiency for the turbine and compressor to be 75%. It's 85%, sorry. Compressor and the turbine isentropic efficiency is given as 85%. So we will, an isentropic efficiency is given as 85%. So we will be using this 85% to find out the actual outlet of the turbine 2, turbine 1 and turbine 2. So the actual conditions of turbine outlets, H2 is going to be greater than H2S because of the irreversibilities. And similarly, H4 is going to be greater than H4S, again because of the irreversibilities. So we calculate the actual H2, the exit of the first turbine, and H4, the exit of the second turbine, and we find them to be higher than the reversible cases. So by using the irreversibilities, we will now find the efficiency to be 45%, which is less than the reversible case. In the reversible case, remember that it was 40%. Here, the reversible case, it was 40%. By the inclusion of irreversibilities, we see that the efficiency of the system has gone down to 35%. And the reason why we have less efficiency here is because of the irreversibilities in the turbines, the first turbine and the second turbine, which are mostly the friction between the steam and the turbine blades, which causes the exit enthalpies of the turbines to be higher. So instead of converting the steam enthalpy to work, some of the energy remains as heat energy, the high enthalpy, because of the friction. There are some modifications to vapor power systems, the uh, vapor systems, power systems, such as using a system called feed water heater. So normally what we do is uh, at the exit of the pump, the water is heated to saturation temperature inside the boiler, then it changes phase inside the boiler, then becomes superheated vapor and so forth. But instead of sending colder feed water to the boiler, it's possible to heat the feed water beforehand, then send it to the boiler at higher temperature. So what is done here is to still use a turbine, a single turbine, but some part of the steam is taken from an intermediate step and it's sent to the open feed water heater. So it means that if we have 1 unit of steam entering the turbine here, some percentage of this 1 unit, let's say Y unit, is less than 1 of course, is separated to be sent to open water heater, then 1 minus Y unit of it continues to produce work inside the turbine. Then the rest of the steam flow is the same. It gets into the condenser, it becomes liquid. Then there are two pumps here. The first pump pumps the liquid at pressure 4 to pressure 5 because they have to be the same pressure. Then the liquid here combines with the vapor, leaving some stage of the turbine here. Then the vapor here heats the feed water to the boiler, and the water comes out of this feed water heater at a higher temperature, then pumped to the boiler at a higher temperature. So let's take a look at here. As you can see, the 2 and the 3 and 5 is combined to have 6. So 2 and 5, 2 is superheated. Here we have superheated vapor. And 5 is compressed liquid, but they have the same pressure because the pump here increases the pressure of the liquid to the same pressure here. So they are mixed inside this feed water heater at the same pressure. So the combination of them, meaning that the liquid 5, which is the exit of the pump, and the steam, which is taken from the intermediate stage of the turbine, is mixed together to obtain 6. So this is the mixture. Once they are mixed, so once this steam and this compressed liquid is mixed to obtain 6, it's then pumped to the higher pressure of boiler pressure. So as you can see, it's pumped to the boiler pressure. Then the rest of the same is the same, and the rest of the cycle is the same. So we have 3 different pressures here. One condenser pressure, one boiler pressure, and one intermediate pressure. let's call it P intermediate, which is this one. So what did we get out of here? By heating the feed water using some part of the steam taken from an intermediate stage of the turbine, its temperature is increased. By this increase, you can see that the area under this TS curve has increased, which is actually the network of the cycle. So by doing this, by heating the feed water, it's possible to increase the total work of the cycle. It's called a regenerative cycle. You have all the relationship between the mass flow rates of the system and their relations with the enthalpies, because at every step you have to have not only a mass balance but also an energy balance. For instance, here you have to have a mass balance of 1 plus 1 minus 1 plus 1 minus y must be equal to, or you can do it like this, 1 should be equal to, 1 is the inlet, 1 should be equal to inlet mass, the two exits, which is y plus 1 minus y. So you can see that you have the mass balance here. Similarly, you can write the energy balance. The energy of the inlet should be equal to energy of the exits. And same for this heater. Once you can write the mass balances and energy balances, you have several equations. You don't have to memorize them. If in an exam or something, you are asked this kind of question, I will provide all the balances, the mass balances and the energy balances. So by using the mass balances and the energy balances, you can calculate the work and the efficiency of a system with an open water heater as shown here. As an example, a numerical example, we have a vapor power generation cycle with open water heater. So the boiler temperature and the pressure is the same as the previous one. So it's still 488 megapascal. Some part of the steam is taken from an intermediate stage of the turbine and it's sent to the open field water heater, and the remaining part continues to produce turbine work. The turbine exit is sent to the condenser, which is at 0.008 megapascal, and it's pumped to the intermediate pressure of the intermediate stage of the turbine, which is given as 0.8 megapascal. So this is the pressure here is 0.8 megapascals, and also the pressure here is the same, 0.8 megapascals. Then as they are mixed inside here, they are pumped to the boiler pressure, which is at 8 megapascals. So we have three different pressures: the condenser pressure, the boiler pressure, and the intermediate pressure, which is equal to the open water heater pressure. The power generated is still the same because we would like to compare this with the other ones. So by using the efficiency of the pump, we can obtain the steam qualities. Once we have the steam qualities, we can use the steam quality to get the enthalpy. So by using, here we are given irreversibilities in the two parts of the turbine. The turbine has an irreversibility so that it has an isentropic efficiency. By using the isentropic efficiencies, we can calculate the actual turbine exit. So the actual turbine exit is this one, which is obtained from the isentropic turbine efficiency. And H3, which is the exit of the second part of the turbine, here, the second part of the turbine, this one or that one, is also calculated by using the isentropic efficiency of the turbine. So the second part of the turbine has an enthalpy of the first pump exit has an enthalpy of 173, and also the second pump exit has an enthalpy of 705. So we will be using them in order to calculate the net cycle work. This is obtained from mass balance and energy balance. You can check the theory of the system, theory of the cycle. So by using the mass balance and the energy balance, the Y, the percentage of the steam that's separated from the intermediate stage is this. So 19.6% of the steam is separated from the intermediate stage and sent to the feed water heater. So Y is almost 20%. It means that 20% of the steam is taken from an intermediate step, while the remaining 80% continues to produce energy, produce pump work, turbine work. So this is 20%, this is 80%, and the value of the Y, the ratio of the steam separated from the intermediate stage of the turbine is calculated as 20%. So by using the energy balance, we can calculate the turbine work for the first case. The pump work is obtained from the value of the Y, and the heat addition also calculated from the mass flow rate of the water, steam. Then we see that the cycle efficiency is found to be almost 37%. It's less than 40% previously, if it's compared to previous one, because of the irreversibilities, of course. So in this case, the required mass flow rate of the steam is found to be 3.69 times 10 to the 5 kilograms per hour. Okay, is the solution of the vapor power cycles clear to you? Okay, let me ask you again. Are the solutions clear? Why are you not answering me? Okay, before starting the vapor refrigeration cycles, we are finished with the vapor power cycles. Now we will start to vapor refrigeration cycles. Let me ask you one more time if you have any questions. Otherwise, we are going to have a break which is longer than 10 minutes. Any questions? Okay, so we'll have a break of almost 15 minutes. Then I'll see you at 3 o'clock. We finished the section regarding the vapor power cycles. Now we will study the section regarding vapor compression cycles or vapor refrigeration cycles. Remember, in Carnot systems, we assume that the system is uh, without irreversibilities, whether it's a Carnot power generation system or Carnot refrigeration system. In the case of a Carnot refrigeration system, we say that there are four irreversible uh, processes. Two of the irreversible processes are uh, constant temperature. So we have two reservoirs, high temperature reservoir and low temperature reservoir, which are irreversible. And also we have another two reversible systems, which are reversible compression and reversible expansion. And they're also adiabatic, which means there is no heat exchange in the turbine and the pump. So in this case, as you can see, we have uh, four reversible processes in a counter refrigeration system. In state one, we have a mixture of vapor and liquid. Of course, we have a refrigerant here, so it's the mixture of refrigerant, vapor, and liquid. Then it's compressed to a higher pressure. So at the exit of the compressor, we have a higher pressure, which is the inlet of the condenser. In the condenser, as it uh, rejects heat to the surrounding, it changes phase from saturated vapor to saturated liquid. So the saturated liquid gets into the turbine, and as it expands into the inside the turbine, which is also a reversible turbine, reversible adiabatic turbine, meaning that the entropy does not change. So reversible plus adiabatic is isentropic. Reversible plus adiabatic is isentropic. So both the turbine and the compressor are isentropic. So inside the turbine, it expands isentropically to the inlet of the evaporator, where heat is absorbed from the surrounding by cooling the surrounding. As it absorbs heat from the surrounding, the mixture is evaporated, not to the saturated vapor, but it becomes drier because of the evaporation. So here we have to we have to provide compressor work, and here we obtain turbine work. This ideal system, which assumes that there are no irreversibilities, but apart from the uh, assumed assumption of irreversibilities, there are some practical problems with the use of carbon refrigeration system. For instance, the compressor cannot be operated with a mixture. So it's better to have the compressor inlet to be saturated vapor instead of a mixture. Similarly, here the turbine cannot be operated with a mixture. So instead of having a turbine here, because the objective of this system is not to generate work, but the objective is to obtain refrigeration. So we can just remove this turbine and put an expansion valve here. So when the turbine is removed from here and an expansion valve is put there, then there will be an expansion like this. Of course, in this case, the entropy will increase and the expansion will be under constant enthalpy. So these are the practical problems of a Carnot refrigeration system. If I repeat, the compressor cannot be operated by using a mixture, so the inlet of the compressor must be saturated vapor, and similarly the turbine cannot be operated with a mixture, so instead of a turbine that will produce some work to be available for the energy requirement of the system, we can just remove the turbine and install an expansion valve, because at the end we would like to reduce the temperature of this saturated liquid to a low temperature so that it can evaporate and absorb heat from the surrounding. So it's not necessary to have a turbine here. We can just install an expansion valve. So when we install an expansion valve, we don't have this isentropic process anymore, but instead an entropy increase, but under the constant enthalpy. In the case of refrigeration cycles, we do not use the concept of efficiency because efficiency is always less than 1. On the other hand, in the performance calculation of refrigeration systems, the performance may be greater than 1 because the performance is always calculated from output divided by input. But for the case of refrigeration systems, the output of a refrigeration system is of course the refrigeration capacity, and input is the work added to the system. So if for the Carnot system, the numerator is cooling capacity and denominator is the net work, which is turbine work minus compressor work. In this case, we get a efficiency of a Carnot refrigerator to be Tc, the condenser temperature in kelvins, they are always in kelvins, divided by Th minus Tc. Tc is the cold temperatures, the lower temperatures, so it's the evaporator temperature, divided by condenser temperature minus evaporator temperature. And it's called beta. So beta is the maximum available coefficient of performance for a refrigerator system, which is a Carnot refrigerator. So we can call it this reversible COP, and reversible COP can be calculated by using the temperatures only. Otherwise, we have to use the definitions of the Q and the work here. So as a general definition, the COP is always Q divided by W, but for the case of a reversible cycle, a Carnot cycle, we can use the temperatures instead of Qs or works. So similar to the power generation systems, there are ways to increase the performance of a refrigerator also. For instance, if the evaporator temperature is lowered, or if the condenser temperature is increased, there will be changes in the COP of the system, because after all, the area under this curve is going to give you an idea regarding the performance of the system. As I mentioned already, the use of a turbine in a refrigeration system is not practical because of the wet operation of the turbine is not so easy. So instead of using a turbine, an expansion valve can be added to the system. With the expansion of the expansion valve added to the system, we get an actual refrigeration system. In an actual refrigeration system, we have four members. The first member is the evaporator, where the cooling takes place. It absorbs heat from the surrounding, meaning that it cools down the surrounding. The exit of the evaporator is saturated vapor, and it's compressed in the compressor to superheated vapor. So at the inlet of the condenser, we have superheated vapor, which is cooled down to saturated liquid. Then saturated liquid passes through the expansion valve to a lower pressure, and as it pressure decreases, it expands into a vapor phase or a mixture phase by absorbing heat from the surrounding. So we have to reject heat at the condenser, and heat is absorbed from the surrounding. This is actually the cooling process. And saturated liquid is expanded into lower pressure where we have a mixture. So similar to the power cycle, there are actually two pressures. One pressure is evaporator pressure, the low pressure, and the second pressure is the condenser pressure, which is high pressure. So for an actual system, we can calculate the heat added or heat absorbed or heat rejected or work added at the compressor by just using the enthalpy differences similar to the power generation cycles. So by using the enthalpy differences, the Q, the heat absorbed in the evaporator is the difference between the evaporator inlet and evaporator exit. So this is Q evaporator, or just we can call it cooling. In the compressor work can be calculated similar to the power generation cycle. It's just the difference between the exit of the enthalpy, compressor enthalpy, and compressor inlet enthalpy. This is the heat rejected. So this is Q rejected at the condenser. This is work added at the compressor. Then I have already mentioned that inside the expansion valve, we have constant enthalpy. So in enthalpy inlet and exit, we have the same enthalpy. So the beta, which is the coefficient of performance or refrigeration system, can be written as the inlet outlet output divided by input. And for a refrigeration system, output is always the Q in, the cooling heat, divided by the work added in the compressor. So here we have cooling divided by the compressor work. This is the TS diagram. This is the TS diagram of a actual refrigeration system, vapor refrigeration system. As you can see, this is the evaporator at which heat is absorbed, meaning that it's QC, cooling energy. At the exit of the evaporator, it's saturated vapor. Then this saturated vapor is compressed in the compressor. This is done by supplying work to compressor. And the exit of the compressor is superheated. Then this superheated refrigerant gets into the condenser. This is the condenser, where heat has to be rejected, QH, so that at the exit of the condenser we have saturated liquid. So, and inside the expansion valve, this is the expansion valve, we have a situation where H3 is equal to H4. Now we will work on a numerical example. According to this numerical example, a refrigerant 134A, this is an HFC. I will mention the types of the refrigerants. A refrigerant 134A is used in a vapor compression refrigeration system, and the cold region is held at 0 Celsius, which is the temperature of the evaporator. So evaporator temperature is 0 Celsius, and condenser temperature is 26 Celsius. You can consider them inside the refrigerator and kitchen, for instance. The refrigerant mass flow rate is given, so M dot is given. We would like to first find the compressor power in kilowatts, the refrigeration capacity in tons. Let me mention what a cooling ton is. One cooling ton is 211 kilojoules per minute, is 1 ton of cooling. So when I say 1 ton of cooling, you should understand that it's an energy rate of 211 kilojoules per minute, or it's also equal to 12,000 BTUs per hour. When you buy an air conditioner system, you will see it on the label showing the cooling capacity. For instance, a small air conditioner would have 12,000 BTUs per hour, which is 1 ton. A larger one could have, let's say, 18,000 BTUs per hour, which is 1.5 ton, and so forth. So we will calculate the refrigeration capacity in tons. Coefficient of performance, which is just output divided by input, and output is always cooling capacity divided by the compressor work. Then coefficient of performance for a Carnot refrigeration system. For Carnot refrigeration system, remember that it assumes that there are no irreversibilities, so you should expect a higher COP for a Carnot than the actual system. So Carnot refrigeration is a reversible system, then it should be greater than the COP of the actual system that we calculate from here. Okay, now we're going to work with kelvins when we calculate the COP of a reversible system. So first we calculate the Celsius temperatures as Kelvin temperatures. So we need to use the refrigerant 134A. The use of the refrigerant tables are exactly the same as the use of the water tables. They have always pressure, temperature, the specific volume, internal energy, enthalpy, and entropy. So the tables are very similar. The first thing is to find the enthalpies that are available in the first place. For instance, you can use this temperature to find the enthalpy here because it's saturated vapor. Also, you can find the enthalpy here at 26 Celsius, which is saturated liquid. So these are immediately available. Besides, you know that because the compressor is isentropic, S1 is S4. Here you can find not only H1 but also S1, which is equal to S4. So from S4 and the pressure of the condenser, you can find H2. What is the pressure of the condenser? You're going to use the saturation pressures. You will go to the table by using the saturation temperature. By using the saturation temperature, you can read the saturation pressure of the vapor. And for the exit of the compressor, you have the pressure and also entropy so that you can obtain the enthalpy of the exit of the compressor. So up to now you have H1, H2. H1 is saturated vapor at evaporator pressure. H2 is obtained from S2 and condenser pressure. Then you have H3, which is saturated liquid at condenser pressure, and we also know that the enthalpy at the exit of the expansion valve is equal to the inlet of it. So as you can see, we have all the enthalpies. Now we can calculate the Q absorbed in the evaporator, Q rejected in the condenser, and work necessary to be delivered to the compressor. So we have first the compressor work to be calculated. These are the values taken from the table, and the compressor requires 1.4 kilowatts. The Q in, which is actually the cooling or Q evaporator, is n dot times H1 minus H4, and this H4, remember that, is equal to H3 because in the expansion valve the enthalpy does not change. So we find the cooling capacity to be 3.67 tons. Then the beta, the coefficient of performance, is found from Q in divided by W, is found from Q in divided by W and is found as 9.24. It means that we get 9.24 times cooling energy compared to 1 unit of compressor work. And also, we can use the reversible COP, Carnot COP, by using the temperatures, and it's greater than the COP of the system, which is expected, because remember that a Carnot refrigerator has the highest COP working at between the same temperatures. So this is expected. There are also some reversibilities in refrigeration systems similar to power generation systems. For instance, the compressor may have some irreversibilities. When a compressor has some irreversibilities, such as friction inside the compressor, friction between the fluid, the refrigerant, and the compressor elements, the moving compressor elements, then we have an increasing entropy. It means that an actual compressor is going to have a larger compressor work than the isentropic compressor. So isentropic compressor has H2S minus S1 as the compressor work, whereas the actual one has H2 minus H1. It means that because of the irreversibilities, we have to deliver more energy to the compressor than the isentropic case. So, an example, the saturated vapor enters compressor at minus 10 Celsius. So, it enters here at minus 10 Celsius, and it exits the compressor at a higher temperature, at 9 bar. Why are we working on this example? Because in this case, you see that the evaporator temperature is lower than the previous one, and condenser pressure is higher than the pressure one, because previously the condenser pressure was like this. Sorry. So this would be the condenser pressure in the previous one, which is less than 9 bars. So we would like to see what happens if we have a condenser pressure which is higher and evaporator pressure which is lower. We would like to see the effect on the condenser pressure and the evaporator pressure on coefficient of performance of the refrigeration system. So in this case, the compressor work is found to be 2.48. So if you compare it with the previous one, the compressor work in the previous one was 1.4. Now it's 2.48. Why has it increased? It has increased because it starts with a lower pressure and ends with a higher pressure. Means that this compressor requires more work than the previous work. That's why, even though the first compressor was 1.48 kilowatts, had a requirement of 1.48 kilowatts work power, this one requires 2.48 kilowatts. It requires more work. So we can already say that this coefficient of performance is lower for this refrigeration cycle, than the previous one because of the definition of it. So because the compressor work has increased, we should expect that COP will decrease. The cooling capacity is now less. It was previously, let's see, it was previously 3.67 tons. Now the new cooling system has a smaller cooling capacity, 3.23 tons. And finally, the COP is less than the previous one. The previous one had a COP of 9 point something. Now it's 4.57. And why do we have a less COP now? Because both the cooling capacity has gone down and the compressor work has gone up. So the combined effect of these two will result in a lower COP. So it means that if you increase the condenser pressure and if you decrease the evaporator pressure or temperature, it will result in less COP. So in order to increase the COP of the system, your evaporator temperature or pressure must be reasonable enough, not too low, and condenser pressure must be reasonable enough, not too high. Now we have an example in which we have some irreversibilities in compressor and in condenser. The compressor has a higher temperature at the exit or higher enthalpy at the exit because of the internal irreversibilities such as friction, and also the condenser temperature is not saturated liquid now, but it's subcooled now. So there is more cooling in the condenser than expected. So what would happen, let's say, if it was super saturated liquid and at the expansion valve, it would come to this point. Then you can see that the cooling effect in this case would be lower than the cooling effect than the second case. Now we will see it with the figures. The compressor's isentropic efficiency is defined as the isentropic compressor work divided by the actual compressor work. So by using the given values of the compressor efficiency, the compressor efficiency is given to you 80%. So by using this 80%, you can find the actual exit enthalpy of the compressor to be 280. So with this 280, you can calculate the heat rejected at the condenser, and it means that the cooling capacity has increased. Why? Because, as you can see, the area has increased when the exit of the condenser is now a subcooled liquid. And now we have a little bit less COP because of the irreversibilities. So the COP of the system is less than the previous one because of the irreversibilities. Is it clear so far, the solution of the compression refrigeration systems? both the color refrigerator and the actual refrigerator. Is everything clear? Okay. So remember that the air conditioner system used for houses can both cool the space and also heat the space. So by using the remote control of the air conditioner device, you can cool the space in summertime and heat the space in winter time. How can you do this? In this case, you're not using the cooling part of the refrigeration system, but you are using the heat rejection of the system. So if the heat rejection system is placed inside the space, if the internal unit of the air conditioner becomes the heat rejection system or condenser, then instead of cooling the space, it's possible to heat the space by the heat rejected by the condenser. When this happens, of course, the coefficient of performance of the system is defined differently because the objective of the system is not cooling now, but heating. So in this case, COP of this is called a heat pump when it's used as a heater. COP of a heat pump is given by gamma. The refrigerator was shown with the beta. This one is defined with gamma, and this time we're going to use as the output as QH, which is the condenser heat, divided by the same W. And it's interesting to see that beta is equal to, or beta plus 1 is equal to gamma, meaning that using an air conditioner system as a heater is more energy efficient than using it as a refrigerator. So how does it happen to operate the same system as both heater and cooler? There is a reversing valve in this kind of refrigerators, this kind of air conditioner systems, a reversing valve. When you push on the operation mode on the remote control, so on the remote control you have cooling and heating. When it's in the cooling mode, the flow of the refrigerant is adjusted so that the dashed flow of the fluid belongs to the cooling mode. In this case, the compressor exit is sent to the outside unit. So this is when the air conditioner used as a cooler. Then the exit of the compressor is sent to the outside unit. In the exit of the outside unit, which is now a condenser, we have a superheat liquid. Saturated liquid. So here we have a superheated vapor. Now we have saturated liquid. As saturated liquid passes through the expansion valve, we have a mixture. Then mixture passes through the internal exchanger, heat exchanger, which is an evaporator. So in the cooling mode, this is the condenser, which rejects heat to the externals, whereas the internal unit is the evaporator, which absorbs heat, meaning that it cools the space. If you push the heating mode on the remote control, then the flow of the refrigerant reversed. So instead of compressor sending the refrigerant to the outside unit, it sends it to the internal unit. Then in this case, the internal unit becomes the condenser, and condenser rejects heat, meaning that it's used as the heater for the inner space of the internals of the space. Then from the condenser, it goes to expansion valve, then outside unit, and it absorbs heat from the surroundings, causing the refrigerant to evaporate. Then it gets into the compressor again. So as you can see, they are actually the same system, except the flow of the refrigerant is reversed. In the cooling mode, the exit of the compressor is sent to the external unit. In the heating mode, the exit of the compressor is sent to the inner unit. So what kind of working fluids are used in refrigeration systems, the compression refrigeration systems? In the past, it was basically chlorofluorocarbons, CFCs, which were freons, So until some decades ago, until 1990s, freons were the only refrigerants, working fluids to be used with the refrigeration systems. But then people found out that the freons are harmful to the ozone layer because they have chlorine in them. And chlorine damages the ozone layer. So since the beginning of 1990s, the use of the CFCs have been banned, and instead of CFCs, now HFCs are used. So in HFCs, there are no chlorine. The chlorine is replaced by hydrogen. So an example to HFC is, for instance, 134A. This is one of the most used recent refrigerants. It's not harming the ozone layer. That's why recently the use of HFCs have increased because of the effect on the environment. So this is the recent working fluid for compression refrigeration systems. And for power generation systems, the most used working fluid is water because it's abundant, it's not harmful to the environment, it's economic. So that's why the use of water as a working fluid in vapor power generation systems is very common. And for the vapor compression systems, vapor compression refrigeration systems, as I said, the CFCs have been banned. They're not being used anymore. They're not being produced anymore. Instead, for instance, HFCs, hydrofluorocarbons, these are chlorofluorocarbons. HFCs are hydrofluorocarbons. They do not have any chlorine in them, so they do not harm the ozone layer. Ozone layer is like a filter for the against the ultraviolet rays. So it filters ultraviolet rays. That's why protecting the ozone layer is important. That's why the use of the CFCs have been banned since the beginning of 1990s. Any questions? Okay, I will announce the details of the exam, the online exam, on the weekend. So uh, you can start studying. Uh, I think the schedule was shared with you. I will also mention in my announcement regarding the uh, day and time of the exam, as well as the details of the exam. So if you don't have any questions, I wish you a good weekend. See you next week.